All right, my clock is showing half past the hour. Thank you all for joining. We are ready to get started. Today, we will be discussing Enviromix's way of equipping aerobic digesters for nutrient removal. My name is Sarah Elger, and I'm our Director of Strategy and Marketing at Enviromix. Our presenter today is Scott Mullinex, Director of Regional Sales. I have a few things to mention before we get started. First, we will be emailing certificates of attendance to all who attend this live webinar. Second, there will be a Q&A period at the end of the presentation, assuming we have time. So please use the Q&A feature on the bottom of the screen, not the chat, to send any questions that you may have. Third, this webinar is being recorded and will be posted on our YouTube channel if anyone wants to rewatch it or in case you have any audio-visual problems. And with that, I will turn it over to Scott to get us started.
Thanks, Sarah. If you've done a virtual Enviromix presentation previously, you may know that we're all about the video calling. But for this presentation, my camera will be off because I'm presenting from the beach in my flip-flops. Unfortunately, no, I won't be on video because I'm relaxing by the pool, but to save bandwidth and reduce those glitchy legs and provide you with the best audio-visual experience. So with that, let's get started. The first item on the agenda today is to go through a little bit of aerobic digestion 101 to get us all on the same page. Then we'll go into the details of Enviromix's Biocycle D process, which also includes our Biomix compressed gas mixing system. Then we'll review two case studies, one from Highland, Illinois, and another from Box Elder, Colorado. And finally, we'll wrap it up with a summary and some questions for me and Sarah. So let's get started with conventional aerobic digestion. Did you know that aerobic digestion is typically the second highest, if not the highest, energy consumer in a wastewater treatment plant? During my nearly 20 years of experience in the wastewater industry, I've seen digesters with higher air demands than actual secondary treatment processes, which doesn't make any sense from an engineering standpoint. Yet, for years, the problem of aerobic digestion came down to the simple premise of blowing more air at the problem. Aerobic digestion can also have significant impacts on the main treatment process because of side stream return loads to the headworks of the plant. But before we get to the Enviromix solution, let's start with a more basic question. What is aerobic digestion? The wastewater treatment process takes raw influent wastewater and uses chemistry, physics, and biology to clean the water before returning it to the natural environment. In the secondary treatment process, microorganisms are used to consume and remove contaminants from the water. The solids treatment is what's done with those microorganisms once they've been removed from the treatment process. Aerobic digestion is a common treatment technology used at small to medium-sized plants for further treatment of waste-activated sludge from the secondary process. The objectives of aerobic digestion are to prepare the sludge for subsequent use or disposal through the destruction of volatile suspended solids, or VSS, and the reduction of pathogens. In the aerobic digestion process, when no primary sludge is added, there is no food added to the sludge, so the oxygen requirement is for breakdown of the sludge only. Volatile solids are removed through a process called endogenous respiration, where some of the microorganisms die and are consumed by other microorganisms. Endogenous respiration is shown by these highly technical chemical equations. I don't know about you all, but I don't remember seeing BOD sub bugs anywhere in my edition of Metcalfe and Eddy. Regardless, as you can see, oxygen is added to the process and the microorganisms break down into less microorganisms, shown here as less BOD sub bugs, carbon dioxide, water, and ammonia. As long as there is enough oxygen, the ammonia is then nitrified to nitrite and then nitrate. Notice that the nitrification process consumes alkalinity, which you'll see the importance of in a little bit. In a conventional aerobic digester process, aeration is used to both mix and aerate the tank to provide oxygen needed for the endogenous respiration. And the solids retention time, or SRT, is typically about 10 to 20 days. Operators usually manually run the process, and there is little to no automated process control. For plants that are trying to reduce the financial burden of landfill disposal of biosolids, they need to treat their solids to meet regulations that allow for land application or other surface disposal. This is known as Class B solids. The relevant Class B regulation in the US is 40 CFR 503. And aerobic digestion can be used to meet Class B solids under this regulation. As I mentioned before, there are two treatment objectives for aerobic digestion: to reduce pathogens and to destroy volatile suspended solids. The Class B requirement for pathogen destruction is focused on retention time at specific temperatures, specifically 60 days retention time at 15 degrees Celsius, or 40 days of retention time at 20 degrees C, or the equivalent pathogen reduction. The requirement for volatile solids destruction is at least 38%, or a specific oxygen uptake rate, also known as a SOUR, of less than 1.5 milligrams of oxygen per liter. This VSS destruction is in place to reduce odors and prevent the attraction of rodents, flies, or other organisms, which is known as vector attraction. Earlier, I mentioned that aerobic digestion is often the highest or second highest energy consumer at the plant. We talk with plants every day and hear about how they are being challenged. Well, they use more colorful language, but challenge basically summarizes their thoughts. We hear about how they're being challenged to make every dollar go further. How can they continue to reduce their operating budget without compromising treatment needs? Well, even though aerobic digestion is such a high energy consumer, usually aerobic digestion is put at the bottom of the list or even forgotten entirely when looking for ways to meet these financial demands. The mindset of throwing air at the issue can be ingrained in our thinking because we don't think there's any other way to do it. So what's the problem with the conventional design? Well, it starts with the aeration system and the difference between what is needed based on the process oxygen requirements and what is needed for mixing. Sometimes the word mixing limited comes up when designing an aeration system. It isn't as common in aeration basins, although it certainly comes up there as well, but you see it all the time in aerobic digestion. So what does mixing limited mean? Within a wastewater setting, aeration does two things. It delivers oxygen to the water and it mixes. Aeration is really good at delivering oxygen, and aeration manufacturers have worked very hard to maximize the oxygen transfer efficiency of their products. The mixing that aeration provides is a side effect of the primary objective of delivering oxygen. That means that aeration hasn't been optimized to mix. As a result, once the oxygen demand is met, it can take a significant amount of additional energy to completely mix the tank. In the design of an aeration system for an aerobic digester, two factors are considered when determining the air requirements for the system. The first is the amount of air that is required to keep the contents of the tank completely mixed. The rule of thumb for this is between 30 and 40 SCFM per 1,000 cubic feet of tank volume. The second is the amount of oxygen that is required for the process, also known as the biological air requirements. Typically, that is around 2.3 pounds of oxygen per pound of volatile suspended solids destroyed. The aeration system needs to be designed for the higher of these two air requirements. Which one will be higher depends on a couple of different factors. It depends on whether primary sludge is being sent to the digester, because the additional food in primary sludge will increase the oxygen required for the biology to do its work. It also depends on the secondary process and how the waste loading and volatile solids destruction due to the sludge age in the secondary process impacts the oxygen required. A longer sludge age in the secondary process is going to decrease the oxygen required for endogenous respiration. To put it another way, if you're running a really long sludge age in your secondary process, then you're burning through all your food and there won't be as much of an oxygen demand left for the aerobic digester. You also end up doing some of the work of digestion in your aeration basins. When that happens, the air demand needed for the biology is less than that required for mixing. That's when we say the process is mixing limited. So what's the problem with the conventional approach to aerobic digestion? Remember, aeration hasn't been optimized for mixing efficiency. The primary concern with the previous approach is the operating budget, and all that excess air being sent to the tanks to ensure adequate mixing really ends up being wasted energy. Let's say in our previous example that the air required for mixing is 1500 SCFM, and the air required for the process is 1000 SCFM. If the system constantly has to operate at the air requirement for mixing, it's operating at 500 SCFM higher than what's actually needed for the biological process. Essentially, you're using 50% more energy than you need to accomplish the treatment objectives. Additionally, when we look at the chemical equation for endogenous respiration, remember BOD sub bugs? We saw that ammonia was produced as a byproduct. When that ammonia is nitrified, alkalinity is consumed. And without supplemental addition of alkalinity, the plant can expect a drop in pH. This low pH and excessive aeration can also result in poor sludge dewatering characteristics, which requires higher polymer consumption. Unfortunately, we see many plants that have aerobic digesters that are mixing limited. Why? Well, the number one reason I see is a plant that is operating at a lower capacity than what it was designed for, resulting in lower loading, not only in the secondary process, but in the digesters as well. Another reason is that digesters specifically are mixing limited is due to the longer sludge ages in the secondary process. These longer sludge ages help with liquid treatment and lowering effluent nutrients, but result in lower oxygen demands on the solid side. Because as I mentioned before, some of the digestion work gets done in the secondary process. The other reason that so many plants are mixing limited is the use of higher efficiency diffused aeration over alternative coarse bubble, jet, or other aeration devices. These higher oxygen transfer efficiency diffusers are great, but remember back to how the aeration system gets designed. It is the maximum of either the air needed for oxygen delivery or the air needed for mixing. And that mixing air rate makes no distinction between aeration device. As a result, all of the energy saved by that great oxygen transfer efficiency is lost because you still need to hit that requirement for mixing. Finally, we also see aerobic digesters that were converted from different tanks that were already on site, like an old primary clarifier rededicated to an aerobic digester. Those primary clarifiers can be much larger than what the system design requirements would dictate would be needed. And those systems are routinely mixing limited as well. Next, I'd like to discuss Enviromix's optimized aerobic digester design approach, which includes mixing that is independent from the aeration equipment. Biocycle D works by alternating between aerobic and anoxic conditions to provide an ideal environment for sludge digestion. The process also offers two alternative modes of operation, selected based on a plant's individual setup. For plants that utilize a belt press or centrifuge for dewatering, there is a sludge processing mode of operation. And for plants utilizing gravity thickening with an automated decanter, the supernatant return mode allows for this type of operation. We will go into each of these in greater detail. During the aerobic cycle, air is provided to the system to facilitate VS destruction. For plants with conical or sloped bottom tanks, or when the air demand is lower than that of the mixing demand, the mixing system will operate at the same time as the aeration system. That ensures the tank remains mixed and that the aeration is able to deliver just the right amount of air without over-aerating the process. During the anoxic cycle, the Biomix compressed gas mixing system ensures complete mixing to create anoxic conditions for denitrification, alkalinity recovery, and pH stability. Cycling between the aerobic and anoxic conditions causes cell walls to rupture, which allows for increased VS destruction and improved sludge dewaterability. That reduces polymer demand and operating costs. As I mentioned earlier, there are two optional modes of operation that are designed to sequester the nutrients in the sludge and eliminate nutrient spikes in the return streams to the secondary process. The sludge processing mode is utilized when sludge is being removed from the tank for further processing. When we were developing BioCycle D, we heard from dewatering equipment vendors who told us that the most important thing for their equipment is consistent flow and consistent solids concentration. Sludge processing mode does just that. This mode uses the mixing equipment to ensure the sludge is homogeneous, which helps regulate and stabilize the polymer addition. During this mode of operation, the ORP readings in the tank are monitored to ensure the process doesn't go anaerobic and allow for P release. If ORP drops below a set point, the aeration is turned on to provide oxygen to the process. Supernatant return mode is used specifically for plants that have an automated decanting device, whether that be with a floating decanter or an automated telescoping valve. Gravity thickening can help increase capacity by thickening the sludge and removing excess water. The supernatant return mode can automatically initiate a decant after a user selectable settling time. The decant cycle ends depending on one of three factors: time of decant, liquid level, or weir position. After decant is complete, the system resumes an aerobic cycle. By sequestering the nutrients in the sludge and reducing the loading to the main treatment process during supernatant return, BioCycle D reduces operating costs for the main treatment process while optimizing sludge digestion. The key to BioCycle D and its ability to optimize aerobic sludge digestion is the decoupling of aeration from mixing. The diffused aeration system is right-sized to satisfy only the process oxygen demand. The basin contents are uniformly mixed by the compressed gas mixing system, independent of the aeration system operation. This opens up a bunch of possibilities that weren't possible with traditional aerobic digestion operation. On the energy side, it eliminates the need to sustain the traditional 30 to 40 SCFM per 1,000 cubic feet design guideline. On the process side, by maintaining the optimal DO needed for the digestion process, BioCycle D is able to recover alkalinity and control pH, reduce plant power bills through oxygen recovery, and reduce nutrient recycle back to the secondary treatment process. The denitrification process can also reduce the proliferation of filamentous bacteria, thereby improving settling, sludge thickening, and overall operational efficiency. By regulating the aerobic phase of the process through DO instrumentation feedback, optimized air delivery and effective digestion are achieved. During the aerobic phase, the blowers operate to achieve the DO set point. Now, we typically recommend that the blowers be on VFDs, which allows for the requested DO concentration to be precisely maintained. However, we can also work with existing infrastructure where there may be blowers without VFDs. That is what we are showing with this data. The blowers at this plant are start-stop controlled. Thus, you see the irregular DO trend during the aerobic phase. Controlling the anoxic phase of the process through ORP monitoring and efficient mixing via the BioMix compressed gas mixing system enables denitrification and alkalinity recovery while reducing nutrient return in the digester supernatant. During the anoxic phase, the blowers shut off and only the mixing system operates to achieve the low ORP set point for denitrification. Once the low ORP set point is met, the aerobic phase begins again and the cycle repeats. The aerobic and anoxic phase cycling minimizes nutrients in the supernatant return, and the process benefits of optimized digestion result in improved sludge dewaterability. BioCycle D operates with repeating aerobic and anoxic cycles. Aerobic cycles are facilitated by the right-sized fine or coarse bubble diffused aeration, and the anoxic mix cycles are facilitated by the compressed gas mixing system. The anoxic cycle is followed by an operator selectable settling and decant phase of the operation to thicken the sludge and return supernatant if desired. Decoupling aeration from mixing allows for independent and optimized control of oxygen transfer and mixing, whereby finer coarse bubble diffused aeration is provided for oxygen transfer, and the BioMix compressed gas mixing system provides efficient mixing. The aeration system is right-sized, and therefore the aeration system operates only for the process oxygen demand, not for mixing. The compressed gas mixing system may operate during the aerobic periods when the air rate is lower than that needed to sufficiently mix the basins. And of course, the compressed gas mixing system will operate during the anoxic phases. BioCycle D is typically designed with 12 to 16 hours of aerobic time per day and 8 to 12 hours of anoxic time per day. It is typical that the BioCycle D aerobic digestion process will operate with less aerobic time and more anoxic time at startup, when the plant is typically at less than design loading, thereby providing further energy savings. One feature of the BioCycle D system that plays a large role in providing optimized aerobic digestion and unparalleled flexibility is the compressed gas mixing system we call BioMix. The BioMix compressed gas mixing system utilizes a rotary screw compressor to supply compressed air based on the system's demand for mixing. The compressor discharges to the receiver tank, which buffers air demand and maintains system pressure. From there, the air goes to the local valve control modules that control the parameters of frequency of firing for each header in the basin, the duration of air release, and the sequence of nozzle header firing. Finally, the air is released from the in-tank stainless steel maintenance-free nozzles. Enviromix provides all the major mechanical components for the system, complete with unit responsibility, and guarantees mixing effectiveness backed up by a field performance test. BioMix operates by introducing short duration 1/2 to 1 second bursts of compressed air fired through the nozzle header system. This creates a distributed bottom-up rolling mixing action. Groups of nozzles arrayed on an individual nozzle header are fired 2 to 3 times per minute to ensure uniformly mixed basin contents. You can see in the video here the changing of the cycles between aerobic, anoxic, and settle and decant. With traditional mixing technology, maintenance is the key challenge. The main issues being hair and ragging of impellers, mechanical seal failure, gearbox maintenance, in-basin oil changes, and general longevity and reliability. Energy consumption is typically about double in comparison to BioMix in an aerobic digestion application. Furthermore, redundancy can be a concern with traditional mixers. When a mixer is out of service, the process efficiency will suffer. Whereas with BioMix, a duty standby arrangement can provide 100% redundancy. Finally, mechanical mixing technology is operationally inflexible because it doesn't allow aeration and mixing to be operated at the same time. However, because BioMix can pick up the mixing requirement, the aeration can be adjusted to match only what is needed to meet the process oxygen demand. Combining compressed gas mixing and fine bubble aeration is at the core of what makes BioCycle D so unique. First are the energy savings. BioMix uses less than 40 to 60% of the energy of traditional mechanical mixing. Second, BioMix requires no in-basin maintenance. Third, and most critically for the digestion process, it allows for simultaneous mixing with aeration at lower aeration rates. And finally, BioMix does not impart significant forces on the aeration grid, unlike point source mechanical mixing, thereby eliminating required reinforcement of the aeration system, the need for clear zones around the mixer, and the potential for damage. BioMix compressed gas mixing also does things that no other mixing system can do. It can mix below the aeration grid, thereby eliminating dead zones, sludge deposition, and the potential for septic sludge. In conical bottom or sloped floor basins, a diffused aeration system needs to be mounted with a common submergence to ensure proper air distribution. However, Because Biomix only fires one header at a time, it is able to mix down into the cone where aeration and mixers can't get. This allows the process to utilize volume that otherwise would have been taken up by settled sludge, and that maximizes basin retention time. We're going to look at a case study on a plant in Highland, Illinois that implemented BioCycle D and see what their experience was. In 2020, the city of Highland selected BioCycle D as part of their wastewater treatment plant upgrade. The project included new headworks, secondary clarification, aerobic digestion, sludge holding, and sludge dewatering. The previous system consisted of inefficient coarse bubble aeration and airlift pumps to transfer sludge between cells in the aerobic digester. Meanwhile, the sludge holding tank had a pumped mix system. The new Biomix equipment included two 25 horsepower rotary screw compressors and three 60 horsepower positive displacement blowers. One of the things that Bill Zimmer, the Highland plant supervisor, especially liked with the BioCycle D system is the simplicity and automation. He was, by his own admission, apprehensive about turning over the keys of the process to a technological black box. But he has been surprised at the lack of issues he's had. The system automatically adjusts the tank's operation based on the loading conditions. They have also seen improvements in sludge dewaterability and VS destruction. Additionally, the plant was given the possibility to operate the basins in series or in parallel. They currently choose to operate them in series, but he appreciates the flexibility to also operate in parallel. Using the conventional design approach of aerated mixing using diffused aeration, 30 SCFM per 1,000 cubic feet of tank volume would have been required. The conventional approach would have required three 200 horsepower duty, two 200 horsepower duty blowers, one for each tank, plus a standby, with two of them running continuously to aerate and mix the digesters. The aeration system for BioCycle D is designed to deliver the required biological oxygen demand with 16 hours of aeration per day, served by a 60 horsepower blower for each digester, plus one spare. In addition, a single 25 horsepower compressor was provided to mix both digesters independently or simultaneously, with a second compressor for 100% redundancy. Actual energy savings seen are nearly 75% over the conventional design approach. Bill was surprised that even though they were treating more flow, they are using less energy than they were with their old system. We're going to look at an example from Box Elder, Colorado. The Box Elder Sanitation District provides service to customers in and around Fort Collins. The district upgraded from a lagoon system to a state-of-the-art wastewater treatment facility in 2013, with an upgrade in 2020 that was focused around both population growth and more stringent effluent limits for nutrients. The plant is currently designed for a 4.6 MGD max month flow with effluent total phosphorus of 0.7 milligrams per liter and effluent inorganic nitrogen of 7 milligrams per liter. Enviromix's BioCycle D was selected as the technology of choice after comparison to a conventional aerobic digester similar to Highland. The solution included two 50 horsepower compressors for mixing energy and three 150 horsepower PD blowers for the aeration. By decoupling the mixing and aeration, the mixing efficiency for the process is about 0.2 horsepower per 1,000 cubic feet. On the energy side, the facility was able to recognize savings of more than $175,000 annually when compared to a conventional aerobic digester that would have required three 250 horsepower blowers for operation, thus driving BioCycle D to be the solution of choice with the lowest total cost of ownership. The plant was also able to eliminate the $400,000 line item on their operating budget by eliminating the need to dredge the former sludge storage lagoon annually. The Box Elder plant manager, Craig Hibbard, was pleased with the minimal localized maintenance offered with BioCycle D, as the only in-tank maintenance is for the diffused aeration system. Along with energy and maintenance savings, the plant has also been impressed with the reduction in nitrogen sent back to the secondary treatment process. The digesters have a decanter so they can gravity thicken right in the digester. That stream is returned to the influent. The pressate from the screw press is also returned to the head of the plant. With the lagoon, the plant often saw high spikes of nitrogen when they decanted. With Biocycle D and the transition between aerobic and anoxic conditions, the ammonia that is released from the heterotrophs can be nitrified and subsequently denitrified. This results in lower levels of both ammonia and nitrate in the return streams. You can see here the lab results of a few samples collected over a 3-month period. All of the results are in the low single digits, whereas it's not unheard of with other aerobic digestion processes to see return streams rich in ammonia or nitrate as high as triple digits. By eliminating nitrogen spikes to the influent of the plant, the secondary process is able to maintain consistently low effluent nitrogen levels. And, as Craig points out, their facility has some of the lowest discharge levels in the state. So that concludes our analysis of 2 Biocycle D installations and how they have solved some of the biggest issues that plague aerobic digestion, namely energy usage and process stability. Now, there was one more thing I wanted to mention. As I was preparing my presentation today, I was reading through the background on Highland, Illinois, and there was one more comment that I felt was important to include. She would never say this about herself, but my co-presenter today, Sarah, is awesome. And Bill from Highland discussed just that with a comment he made about how Sarah went above and beyond to help during startup and operation. Biocycle D is a great process, but it's the people at Enviromix that make all the difference. So to summarize the benefits of the Biocycle D aerobic digester, we first focused on the terrific energy savings, typically around 50 to 75% compared to conventional designs. The energy savings come from the separation of aeration and mixing equipment, which allows the system to deliver only the air that is needed. Biocycle D also encourages nitrification and denitrification by creating an operating cycle that adjusts automatically based on the system's demand. Finally, the integrated solution ensures that the plant is fully supported for years to come. We at Enviromix pride ourselves on providing solutions that meet our customers' needs. Our suite of products includes Biocycle D, Biomix, and the 2022 WEF Innovation Award winning Biomix DC, which will be the subject of an upcoming webinar this spring, so stay tuned. These products and more provide process and mixing solutions designed to increase energy efficiency, ensure straightforward operation, provide process optimization, and guarantee unparalleled flexibility in a wide range of water and wastewater applications. Thank you for your time. Feel free to submit your questions using the Q&A feature.
Thanks, Scott. We do have a couple of questions already flowing in. I'll send a few your way. The first one, if you wouldn't mind answering, is how are the cycle times controlled? Is it based on time or just input from the instrumentation?
Yeah, okay, so great question. The cycle is controlled primarily based on input from the instrumentation. During the aerobic period, the DO probes control the blower, either through a VFD or start-stop operation, like we saw in the one graph earlier. And the ORP sensor tells us when the oxidizing work has been completed. Once we see that the ORP has reached kind of a plateau where all the oxidizing potential has been obtained, that's where we transition to an anoxic period. During the anoxic period, we monitor the ORP, and when it reaches a min value, then we know that all the nitrates have been denitrified. And in order to avoid going anaerobic, that's where we'll switch back into an aerobic period. An anaerobic period is where you might get phosphorus release from the sludge, and we don't want that to happen. So we use a minimum set point for the ORP, in order to transition back to the aerobic cycle. So that's the primary method of control, is the instrumentation. The time runs in the background. And so it acts as like a governor on the process, preventing the system from being in one type of condition for too long. So there's two levels of control: instrumentation as the primary method, and then there's a time-based cycle that kind of runs in the background and keeps everything moving along.
Great, thanks. We have a question specifically about biomix. It says, so the compressed gas is just compressed environmental air. Can you clarify that?
Yeah, so a little bit on nomenclature. So compressed gas mixing has been spoken of in the industry also as large bubble mixing. But when people would hear large bubble, they would think, oh, like coarse bubble, fine bubble, coarse bubble. It's like aeration, right? Not really, because the large bubble aeration, or what we're calling compressed gas mixing, is not designed to transfer oxygen. Fine bubble, coarse bubble, those are diffusers that are designed to transfer oxygen into the liquid. Whereas the large bubble mixing is not designed to transfer oxygen. And as a result, it can be used for anaerobic, anoxic environments. So typically the compressed gas is compressed air, but the system can also be used in anaerobic digesters. So that's why we keep the option open in order to allow for compressed air or compressed biogas from an anaerobic digester. So to directly answer the question, typically, yes, it is just compressed air, but it doesn't necessarily have to be.
Great, thank you. We have a question about retrofitting. Can you just add the compressor system to an already existing aeration system, or does the whole digester have to be redone?
Another great question. We can work with an existing aeration system. Typically, what you'll see is a lower air requirement that's needed. And so a lot of times we will look at the loading and make a judgment call based on how many diffusers are there, whether we need to, whether it would be advantageous to plug some of the diffusers based on the air rate that the process is going to demand. It certainly can use an existing blower and existing diffusers in a tank. The compressor, receiver, valve module, and biomix headers can all be added around an existing aeration system.
Perfect, thanks. We have a couple of detailed questions about some of the case studies. We'll send you guys a response via email after this with some of those details. One of the other questions we have here that I wanted to get out though is, does Enviromix provide the decanter?
We certainly can provide the decanter if asked to. It's kind of on a case-by-case basis. Usually with an automated decanter, so like an actuated telescoping valve, that is something that our panel can control. If it's a manual decant device, normally that would then fall outside of our scope of supply. So it can, short answer is that it can go either way, depending on what is best for the plant and best for the project.
Okay. We have a question here that I'm going to answer. It says, great presentation, lots of good information. How can we get a copy of it? This webinar was recorded and will be posted on our YouTube channel. You will get a link to how to rewatch that in your email. Also in that email will be a certificate of attendance and some links for the 2 case studies that we presented. Let me see, we're just about out of time. Let me find one last question here. There's so many great questions. Thank you all for these. One is the gas mixing system running at the same time as the aeration?
Short answer is that it can be. And that's really what's most important. So we can have the system or we can do the calculation to determine what is the mixing limited air rate based on the volume of the tank. What do we need in order to deliver that 30 SCFM per 1,000 cubic feet that's needed for mixing? If the airflow meter indicates that the air rate is above that level, we can turn the compressed gas mixing off to that tank, making maximum use of the energy that we're using. When the air rate drops below that threshold, we turn the compressed gas mixing on in order to ensure that the tank is completely mixed. In a tank with a pretty severe sloped floor or conical bottom, where there may be a significant volume that's sitting below the diffused aeration system, there we would likely keep the compressed gas mixing system on all the time in order to ensure that we're not getting sludge deposition below the diffused aeration system, and so that we can fully maximize the volume of the tank and contact the entire biomass with any kind of influent that's coming in order to keep everything well mixed.
Great, thanks. We do have a couple people asking about whether we have any installations near them. They have some specific areas listed. I would recommend, we will get back to you specifically, but anyone that's interested in seeing any of our other case studies for Biocycle D or any of our other products, please feel free to hop over to our website. We've got a way that you can sort by different areas within the United States and also be able to sort by product or by application. And so if you'd like to see any case studies on those are there. We also have an installation map that shows our installations pretty much all throughout the United States. I think there's maybe 1 or 2 states that we don't have one in quite yet, but we're getting there. With that, we are over on time, and we do plan to respond to all of you that submitted questions. We appreciate your thoughts and your questions, and we will get back to you one-on-one via email. As mentioned, you will receive an email after this that gives you your certificate of attendance, and we thank you all for attending. We really appreciate it. Great job today, Scott. Thank you.
Thank you, everybody.